Coming to you from Oklahoma State University, my name is Josh Klingman, team lead for this year's Argonia Cup 2024 Senior Capstone Design Team. The Space Cowboys have 12 team members this year, spread across 3 sub-teams. For this competition, we will be breaking new ground, launching the first 100% scratch-built rocket constructed at Oklahoma State University. Our rocket, Rango Mk1, was designed to be very competitive in hopes of bringing the Argonia Cup back to Oklahoma State once again. This year's mission for the Argonia Cup is to take a payload of as many golf balls as possible to the highest achievable altitude. We attack this mission by designing weight-saving structures, optimizing our payload, and innovating vehicle construction. The Space Cowboys consist of 3 sub-teams: Aero, Structures, and Avionics. Our Aero team includes Jarrett Schwartz, Charlie Fett, Jordan Block, Nick Sweeney, and is led by Ben Klingman. Our Structures team includes Caden Mincy, Tommy Hosty, myself, Josh Klingman, and is led by Brett Winter. Our Avionics team includes Natalie Thornton, Logan Thornton, and is led by Robert Paddock. I will now pass it off to the rest of the team to introduce our design process and concepts for this competition.
My name is Ben Klingman, and my role for this project is to help lead the Aero design team to design and fabricate all the necessary components for our rocket. For our mission, we are constructing a kit fiberglass rocket, and we're working to construct a scratch-built rocket with in-house wound tubes and custom flat plate pieces for composites. Our flat plate production has been standard flat plate layouts, pulling a 24-hour vacuum for each plate. We then take each of those pieces to a water jet, and using a SolidWorks DXF file, we obtain precision-cut pieces for the build. This allows us to manufacture all of our bulkheads, our centering rings, and our fins in-house at a very low cost with any material that we desire. Since we are producing composites in-house, the strength of our materials is critical. More importantly, the validation of the material strength under our specific flight conditions. The Aero team has been working hard to test and collect material strength data for our report and our project validation. Building our simulation, we can override each mass with our manufactured materials and determine what the optimal flight conditions are for the vehicle. Our simulation was also integral in determining the size of our payload. The Structures team and the Aero team have collaborated on our payload design, interfacing with our rocket design to ensure a safe flight.
My name is Jarrett Schwartz, and my role in the Aero team has been in fabrication and finishing of our house-made flat plates and wound tubes. Using OpenRocket, the Aero team used the final rocket design and held a competition to design the best fin shape. By iteratively changing the geometry, the team found the design that resulted in the best altitude. However, OpenRocket does not simulate wave drag effectively, so to confirm the designs we optimized in the OpenRocket simulation, we imported the geometry to SolidWorks and performed CFD. This analysis generated drag profiles on each fin, and these values were paired with the fin's altitude gain. Comparing across several fins, a final design was chosen for best performance across both simulations. This final design was slightly changed during construction as it was unable to be routed and beveled to the edge our group wanted. Like the fins and centering rings, the bulkhead lids were also cut from our house-made flat plates and were routed to create a stepped edge to enclose each bulkhead section. While the water jet creates accurate parts, they are not all uniform across edge finish and thickness due to variability in our flat plates. To ensure a smooth construction and launch, every part requires many sanding passes, either by hand or assisted on a lathe.
I'm Charlie Fett with the Aero design team. Our team utilizes an X-winder in the making of our tubes. The process begins with placing a filament toe onto the X-winder. The filament is fed through a set of rollers at various locations of the machine to maintain tension and keep the filament laid out flat. With the filament loaded, the team inputs different design parameters into the X-winder's design software. The number of layers, winding angle, and the end cap angle allow us to completely customize the tube wind to precisely control the filament pattern. The machine makes a pass by laying out filament as the mandrel spins, moving to the end of the mandrel, then back. Based on the mandrel geometry, the software determines how many passes are needed to cover the mandrel completely. The preparation of the mandrel was its own unique problem to solve. Our method of winding utilizes 3D printed mandrels to wind around. The recommended method did not work with our 3D printed mandrels. So after much trial and error, we settled on a particular method of lubrication and vacuum bag release. Preparation starts with applying a thin layer of lube across the surface of the mandrel, and after that layer is evenly spread, a vacuum bag is applied to that surface. That process is repeated to ensure the wine can be slipped off of the mandrel without any trouble at all. A layer of mold release wax is then applied to the outer vacuum bag so the epoxy doesn't bond to the mandrel. Once the wine is finished, one last vacuum bag is applied and heat shrink tape afterwards to compress the epoxy. This is how we fabricate tubes in-house for this competition.
Hello, my name is Brett Winter, and I'm the Structure Sub-Team Lead. I'm in charge of overseeing the payload design, construction, and integration into our rocket. Our payload section is split into two equal sections to equally balance the weight and maintain stability across our sustainer. The two payload sections will be separated by our sustainer eBay and drogue parachute. The main design parameters we considered for our rocket was 1. Static stability across the rocket, 2. Dynamic stability with emphasis on vibrational issues, and most importantly 3. Deciding the amount of golf balls we can carry and integrate safely into our rocket. The payload design was comprised of 3 initial ideas, including an open section, closed section, and a modular jig. After different stages of testing, the closed section was removed from consideration due to the poorer performance compared to the open design, with no real securement upside. Further testing revealed that the open section was too big of a stability risk. Therefore, the jig was selected to iterate and reduce the weight, increase performance, and maximize the golf ball load. The remaining structures team members will elaborate on the vital structural components of the rocket.
Hello, my name is Tommy Hosty, and I'm a member of the Structures Sub-Team. The team decided to utilize a boat tail design on the aft section of Rango to reduce drag. The boat tail screws onto the end of the motor mount via a motor retainer cap connection. Due to the scratch-built nature of Rango, our boat tail must also be made custom as well. The boat tail has been 3D printed and then will be glassed with composite material to ensure it is sturdy enough to withstand multiple flights. Boat tail design is optimal at higher speeds than our vehicle will go, but Rango will still experience a reduction in drag from the design.
Hello, my name is Caden Mincy. The nose cone design was sized to fit the desired 150-inch parachute. It is comprised of 3 components: an aluminum nose cone, a drafted subsonic design section, and a tube section. The drafted section and the tube section will be glued together and will encase the 150-inch parachute. The aluminum nose cone will slide into the forward part of the drafted section and will have an eye bolt connected to the aft face. The eye bolt then connects to a quick link that connects to the shock cord. The shock cord connects to the whole parachute system. The parachute is protected during flight by a Nomex heat shield to reduce the possibility of the parachute becoming compromised. The nose cone design consists of key components such as custom dimensions and design to minimize wasted space while allowing quality clearance for the parachute to slide out. Additionally, the complete nose cone piece will eject from the sustainer body tube and rely on its own parachute to safely reach the ground at 20 feet per second.
Hello, my name is Jordan Block, and I'm a member of the Aero Sub-Team. Computer-aided design software played a vital role in the rocket component production, facilitating the design, construction, and validation processes. Our team utilized SolidWorks to design various parts of the rocket, including the payload jig, electronic bays, nose cone molds, and fin jigs. The utilization of CAD software enabled our team to quickly generate prototypes and obtain physical rocket components, which allowed for quick identification of component strengths and weaknesses and expedited the design process. Finally, modeling all components within CAD software allowed for the creation of the entire rocket assembly in the software. This comprehensive model was invaluable in validating part dimensions, providing an illustration to the team of the final design, as well as helping the team identify integration challenges of parts that may not have been identified without the model.
Hello, my name is Robert Paddock, and I'm the Avionics Sub-Team Lead. My team members are Natalie Thornton and Logan Thornton. The role of the avionics team is to design and build the systems that control the various functions of the rocket, such as stage separation, motor ignition, parachute deployment, and recovery. Our rocket will utilize 3 separate avionics bays positioned throughout the rocket, which will each control different aspects of the rocket's flight. The avionics bay housed in the booster will control the recovery of the booster stage. The avionics bay in the sustainer will control the separation of the 2 stages, the ignition of the sustainer motor, and the drogue parachute deployment, and the nose cone avionics bay will control the main parachute recovery stage at the sustainer's apogee. The avionics bays will be 3D printed and housed within fiberglass couplers held together with steel all-thread and composite end caps.
Hi, my name is Natalie Thornton. As a member of the avionics sub-team, part of my job is to find a way to recover the booster safely. Our booster will separate with our sustainer using the telemego with a time-based ejection charge followed by another single redundant charge to ensure separation. After the separation from our sustainer, an Easy Mini will deploy the booster main parachute ejection charge at apogee, followed by a single redundant charge. Our booster main parachute has a 100-inch diameter to allow a ground strike velocity under 20 feet per second. Like the parachute in the nose cone, this one will also be protected by a heat shield so that the charges don't cause damage. To aid in recovering the booster section after launch, we have equipped it with a radio frequency transmitter as well as a built-in GPS tracking in each avionics bay.
Hi, I'm Logan Thornton, member of the avionics team. Following separation from the booster, if all sustainer logic is met, the sustainer motor will ignite and propel the sustainer to apogee. Immediately following apogee, the sustainer drogue ejection charge will separate our payload section and our drogue parachute will be released. After the initial drogue separation, a single redundant drogue separation charge will ignite. Post-drogue separation, at a specified altitude, our sustainer main parachute charge will deploy and the main sustainer parachute will be released. Following the main parachute deployment, a single redundant charge will ignite. Our sustainer drogue parachute and main parachute were sized to 50 inches and 150 inches respectively to allow for a ground strike velocity under 20 feet per second. The sustainer is also equipped with radio frequency and GPS tracking to aid in recovery. Our ground station will be equipped with a radio frequency receiver and GPS tracking antennas.
Hi, I'm Nick Sweeney from our Aero Design team. For more information about our project and some additional information about each member of the team, visit our website linked below. We would like to give a special thank you to our project advisor Zach Wattenbarger and our project professor Dr. Jamie Jacob. Additional thank you to our supporters Monster Energy, Decom Composites, and Iron Monk for providing us with materials to keep the project going and unique marketing opportunities. Finally, we would like to thank Oklahoma State University Mechanical and Aerospace Engineering Department for giving us the opportunity and funding the project.